Right, year 12. This is Mr. Mumford from his shed. I'm going to have a go. I'll try and make a video and I'm just going to see how it goes. And anyway, if I was with you, what's today? Today's Wednesday. I would have had your lesson today. We've done 2 lessons, but unfortunately we've not been there. Anyway, so what I'm trying to do is trying to show you what I would have done this week, and it's a test. I'm not going to do it all video. I'm going to do a bit of video. Anyway, we'll be working on with the state definition of mechanical electromagnetic waves, definition of longitudinal transverse waves, and then I would define displacement, amplitude, wavelength, time period, frequency. Use the equation T equals 1 over frequency, and use the equation C equals F lambda. Describe what's meant by polarization, unpolarized, and plane polarized waves. I know that if a wave can be polarized, then it must be transverse wave. And describe what happens to light intensity rotate 2 polarized filters through 360 degrees and explain why this happens. Now that is on a video that I've uploaded on Edmodo. You'll be able to see that, so I probably couldn't do that now, but I'll see what I can do. This is mainly a test to see if this damn well works. State 3 examples on mechanical wave and electromagnetic wave. Well, mechanical wave is dead easy. Mechanical waves, there must be a disturbance of particles. It could be sound wave, water waves, for example. Something physically must vibrate to basically produce mechanical wave. Mexican waves, in football stadiums when they're ever open up again. Example, mechanical wave. Now, the electromagnetic waves, we do know because you've done light waves beforehand. And to remind you, because I did talk to you about it, you're basically involving 2 fields where you have here an electric field, which vibrates up and down that way, and then you've got a magnetic field. And we now know you can't have an electric field without a magnetic field, and they're always perpendicular to each other. They transfer energy, you know that, because basically light waves go into your eye, your retina picks up the energy they transfer. And you see electromagnetic wave there. Anyway, that's what electromagnetic wave is. I've obviously done that beforehand. And then you should have done this at GCSE, and this is all about transverse wave and longitudinal wave. If I was with you, I'll be actually using a slinky to do this, but I'm not, am I? And these are traveling waves. Now, it's a lovely bit of ancient software. Now, transverse waves is when you have got something oscillating, but it's perpendicular to the direction of the wave. So you can see waves going left to right, my computer screen here, and the particles vibrating vertically up and down. Therefore, it's basically, we define transverse wave as vibrating perpendicular to the direction of the wave. Oppositely, you've got a longitudinal wave down here. And a longitudinal wave, again, the wave is going from my left hand to the right hand side of the screen, but the particles going back and forth and they're vibrating left and right. In other words, they're vibrating the same direction of the wave. Now, if I freeze this, can I freeze it? Yay. Things you did at GCSE you know about is from here to here is basically, we call that the wavelength, which is the top of the wave to the top of the wave. It can also be here and here. Now, these 2 parts of the wave need to be in phase. I'm going to talk about phase. I'll probably make another video, to be honest, with phase. Now, a longitudinal wave, you can see here the wave's stretched out, and here it's compressed, stretched out and compressed. We call these horrible word refractions, and they are compressions here. Now, the wavelength now, here is exactly the same wavelength of transverse wave, and here you've got a compression just here to another compression here. Therefore, again, that's the wavelength. Now, it's really hard to show the amplitude on the longitudinal wave, and the transverse wave is dead easy. It's the midway point, which is here, to maximum amplitude, or the midpoint way here to the bottom of the wave. On this one here, it's roughly back and forth like that, and it's really, really hard to show. But if I set it off again now, if I make the amplitude smaller, you can see these vibrate back and forth, nowhere near as big. If I crank up the amplitude again, you can see now they're back and forth really big. I can also, very excitingly, I may be excited by this, change the wavelength. And now you can see the waves are more squished up. And you can really see now the compression is traveling on the wave going across. Quite hypnotic, really, isn't it? But what I want to see, and this comes up later on, if you actually change the frequency of the wave, you notice the wave speed changes. And you change the wavelength of the wave, you see the wave speed changes. In other words, the wavelength goes down, the wave speed goes down, and the frequency goes down, also the wave speed goes down. And that's the equation we've been using in the first unit. Anyway, very exciting now. Now, these I've just been through and defined the different parts. Is the amplitude wave, we say it's the crest to the crest. And what we say, it is basically going to be two parts of wave that are in phase. Time period is time it takes the wave to one complete cycle, up here, to there, to there, to there, and back up again. Displacement is basically at any time how far the particle is away from the equilibrium position. Time period, as mentioned before, complete cycle, and frequency is a number of complete cycles per second. That's measured in seconds, and that's measured in hertz. These are all measured in meters, because they're all a distance. Now the wave equation, I'll have a go, I'm going to try to write this, is V. I'm waiting to get my flash little pen from school when I haven't got it yet. Therefore, I'm trying to do this with the cursor. Believe me, it's very, very hard. I haven't got a blooming mouse either. V equals F lambda. Now, what you've done is now you know you do C equals F lambda, just like that, where C is going to be the wave speed of electromagnetic wave, which remember is 3 times 10 to the power 8. Now, where this equation comes from is dead easy. If you've got this wave going up and down, F is the number of cycles per second. So you think about it, if you've got 1 hertz, that's going to be 1 cycle every second. Oh dear, trying hard on this. If you've got 2 hertz, then going to be 2 cycles every second. So this wave is going up and down. Now, in other words, if here is going to be time 0, and here is going to be a time later, and the time is going to be 1 second. This is hard work, believe me, it's hard work using a cursor. I know that wave is going to go up and down F times later. And if you really think about it, the distance it travels is going to be F lambda. Because what's going to happen is, if you've got a frequency of 1, it's going to go only 1 wavelength after 1 second later. It's got a frequency of 2, isn't it? 2 wavelengths. Now, you know your velocity is simply going to be your distance over time. Oh dear, trying hard here. There you go. Therefore, if you really think about it, say time is going to be 1 second, I know the wave is going to travel F times lambda forward, which is going to be the distance. Therefore, that's where V equals F lambda comes from. And obviously V is taken away with the C symbol. We've got electromagnetic wave. They may ask you that proof, maybe not. But I mean, it just really it comes from, it basically is use equation distance equals speed. Sorry, speed equals distance divided by time. Therefore, I know how far it's going to travel. It's going to be F lambda. But we've been using that already, and we're quite happy with it. The interesting thing comes in here is all about polarization. Because if we go back to electromagnetic wave, the main part of the electromagnetic wave that interacts with substances is really the electric field. The magnetic field doesn't do much. Electric field makes electrons move up and down in substances. So what it does, it transfers the energy. But what we could have is unpolarized light. So imagine one stage, the electromagnetic wave is going up and down like that. Then it go like this, and then go like that, and it can keep changing its direction. And what you can do is you can polarize it so it only vibrates in one direction. Now, to help you with this, I'm going to show you this bit of software. So here, these are polarized. Now, what they mean by that is they only allow the wave to vibrate in the vertical plane. So if I send a wave through here, this wave is unpolarized and vibrate any direction you want. As soon as it goes through that first polaroid, it only wants to go in the vertical direction. But that wave was trying to vibrate horizontally. Therefore, it can't get through because it only allows vertical vibrations. So if I pause it here and rotate number 1 and rotate number 2, oh, but they was on as well. There you go. If I send a wave through now, is it going to arrive? No. Oh, there you go. This wave is vibrating in horizontal plane. That will allow it through because it's in the same orientation, and that will allow it through as well. So you can actually make light polarized, going to be vibrating all different directions. This only allows vibrations through the horizontal plane. But this one here, and this is the interesting part, if I turn that one so it's vertical, this one lets it through, but this one won't because it's only vibrating horizontal plane, and that only allows the vertical through. Therefore, it blocks it. And this is how the polarized work, and I'm quite sure one of the videos I put from Flipped Around Physics shows you turn this polarized and the whole thing goes black. And here we go. It's very exciting. Here we go. Horizon go through, but that's more explained. But you do need to know about waves can be polarized. So that is the polarization part of it. And I'm going to end this video now here and see if this thing actually blasted works. Okay, this is Mr. Mumford signing out.